Welcome to the deep dive. So, if you've been watching the AI landscape lately, and I mean, we know you have, you've seen this massive shift.
Oh, absolutely.
Large language models, they've stopped being just, clever chat partners. They've really transformed into what we're now calling AI
Right.
agents.
These are systems that are far more sophisticated. They're equipped with reasoning, planning, perception, and this is the crucial part, the ability to actually use tools.
And that transformation, it just fundamentally changes the game when you go from a single back and forth chat to an agent that has to plan and execute these multi-step goals. There's one component that really defines its success or
Yeah.
its failure.
And that's memory.
Memory has really emerged as the cornerstone capability, hasn't it? It's what underpins that long horizon reasoning and lets an agent adapt as it interacts with these really complex, changing environments.
It does. But here's the problem, and it's one we found all over the
That's
sources.
so.
It's something every developer is facing right now. The field has become, well, conceptually fragmented.
Exactly. You hear all these terms flying around: declarative memory, episodic, parametric.
And they're all used so loosely across different papers and projects. So our mission in this deep dive is to try and bring some order to that chaos.
Okay.
We are going to cut through the ambiguity using a systematic three-pronged framework. We're going to look at agent memory through its forms, functions, and dynamics.
A unified field theory for AI memory. I love it. So before we get into that structure, let's just establish the technical boundaries. We're talking about the agent loop, right? That's the core process.
That's where it all starts. The agent loop is observation, then an optional memory retrieval step,
Okay.
followed by the LLM's computation, which leads to an action. Then you get feedback from the environment, and finally, another optional memory update.
So that retrieval and update mechanism, that's the key.
That's it. The formation and evolution of that persistent state is what truly defines a dedicated agent memory system. It sets it apart from just having, really big context window.
Okay, let's unpack this immediately because I think the confusion here is rampant. When we say agent memory, how is that different from concepts you've probably heard of everywhere, like internal LLM memory or RAG?
Right, it's a critical distinction. It's kind of the difference between the car's engine and the driver's logbook.
Okay.
Think of LLM memory as being strictly about the internal architecture. It focuses on the model's own dynamics, like managing the transformer's key value, the KV-CAC.
The little scratch pad it uses for a single thought?
Exactly, just during a single run. Or it could be architectural tweaks, like in models such as Mamba or RWKV, that are just designed to hold on to information better as the input gets longer.
So that's all about model capacity, how long the model can kind of hold a thought in its head during one query.
Precisely. Agent memory, on the other hand, is almost always an external evolving scaffold. It's focused on maintaining a persistent and self-evolving cognitive state.
One that lasts.
One that endures across sessions, across tasks. It lets the agent track your preferences, remember past failures. It truly supports cross-task persistence. Systems like MemGPT, which can track a dialogue state over months, that's a prime example.
That distinction capacity versus persistence, that's really key. So now let's tackle RAG, retrieval augmented generation. We know RAG is great for grounding facts, but how does it contrast with this persistent agent memory?
Well, traditionally, RA is all about augmenting an LLM with access to static knowledge.
Like an encyclopedia.
Exactly. Documents corpora. Its job is to reduce hallucinations. The knowledge base is fixed, it's used for a single task, and it doesn't change based on the interaction.
But wait, I have to jump in here. We're seeing systems like agentic RAG and self-RAG now, where the system updates itself. So is that static versus dynamic distinction still holding up?
It's absolutely blurring, you're right. But the core distinction is still there, and it's about intent and scope. Agent memory operates within an agent's ongoing life cycle with an environment. It's continuously incorporating new information from its own actions and feedback. It's building an experience base. RA is focused on fact retrieval. Agent memory is focused on building an internal, personalized biography.
Okay, so agent memory is dynamic and experiential. RG is traditionally static and factual. Got it. So finally, what about context engineering? This sounds a lot like managing working memory.
It is. Context engineering is really a methodology that treats the context window as a constrained computational resource.
It's resource management.
Yes, exactly. It's about optimization. You see techniques like token pruning, something like scissor hands, which acts like a digital janitor, cleaning out less important tokens to make room for new critical input. That's context engineering.
And agent memory is the cognitive resource itself.
Yes. Agent memory defines the cognitive scope. what the agent knows, what it's experienced, and how that evolves. The two fields meet at that short-term working memory level, where context engineering makes sure the agent's current thoughts actually fit inside the box.
Perfect. So now that we've kind of placed agent memory in the landscape, let's get to the core of this. Let's talk about its forms.
Right. What architectural or representational forms can this memory actually take? We've identified three dominant physical realizations.
Okay, the nuts and bolts. Let's start with the one that feels most, I don't know, human, explicitly recorded data.
That's token-level memory. This is where you store information as persistent, discrete, externally accessible units.
So raw text, logs, that kind of thing.
Exactly. Raw text, visual tokens, logs. And because they're explicit, this type of memory is highly transparent, it's easy to edit, and crucially, it avoids catastrophic forgetting. You can always go back and read the log.
And the sources break this down by topology, right? The structure determines how smart the retrieval can be.
Exactly. The simplest form is flat memory, which is 1D. Think of it like a receipt log or just a simple chronological diary.
Oh, well,
The simplest. It's just an accumulation of sequences. Systems like MemGPT's dialogue logs or the experience trajectories and reflection use this. It's great for broad chronological recall, but it suffers from massive redundancy and, it has no relational understanding.
So if I ask it what I bought last Tuesday, it's great. But if I ask how last Tuesday's purchases relate to my overall diet.
It struggles, precisely. And that's why we move up to planar memory, or 2D.
Okay.
This introduces a single-layer structured organization, usually a tree or a graph. Think of it as turning that diary into a massive mind map. It captures relational dependencies, linking entities, concepts, experiences.
So it connects the dots.
It connects the dots. Systems like AMEM or Memoria use this to enable much more structured lookups and relational traversal. It vastly improves contextual knowledge.
So 2D memory solved the relational problem. But what's the next bottleneck? Why do engineers need to move up to something like hierarchical or 3D structures?
Scale and complexity. Without hierarchy, all your memories just consolidate into one massive single graph. And when an agent has thousands of experiences, querying that one giant graph becomes incredibly inefficient.
It's overwhelming.
It's overwhelming. And that leads us to hierarchical memory, or 3D. This is all about organizing memory across different levels of abstraction.
So it's like an org chart for your memories.
So that's a great analogy. It organizes information across multiple layers, forming a volumetric or stratified memory space with links between the layers. The low level has detailed events. The middle level aggregates those into summaries. And the top level tracks overall goals and themes.
And systems are actually doing this.
Oh, yeah. Systems like GraphRag or HiAgent's goal graphs do this. They aggregate these low-level subgraphs into high-level summaries. This allows the agent to navigate vertically, zoom in for details, zoom out for context. It leads to extremely precise retrieval.
That makes a ton of sense. Okay, so moving on from explicit storage, we hit parametric memory. This is where memory is stored implicitly, right? Inside the model's weights.
Yes, stored directly within the model's parameters, accessed implicitly during a forward pass. It's truly learning, not just recording.
And there are two subforms here.
Right. First is internal parametric memory. This is encoded within the original weights and biases.
Yeah.
You use this for injecting deep domain knowledge or long context priors during pre-training.
So like fine-tuning a model to become a specific persona, maybe like character LM, to memorize a user's history or voice.
Exactly. Think of it like deeply ingraining a skill, like learning to ride a bike. It's fast and inherent once you've learned it, but you can't easily unlearn it or teach it a whole new conflicting skill.
Right, you risk messing up the old one.
Precisely. And that's the major downside. It's costly to update, and it risks catastrophic forgetting of old knowledge when new information is absorbed.
And catastrophic forgetting is a huge barrier for any agent that's meant to live for a long time. So how do they get around that?
That brings us to the second form, which is external parametric memory. This is the compromise. Memory is stored in these auxiliary parameter sets. Most commonly, you'll see adapters or Leroy modules.
Ah, okay. So instead of trying to retrain the entire brain, you just bolt on a new specialized skill module.
That's a perfect analogy. Systems like KDapter or Elder, they use multiple Leroy modules to inject new knowledge or skills without destabilizing the base model. You get the generalization benefits without the catastrophic forgetting risk.
Okay, that makes sense. So our final architectural category is latent memory. This one sounds like the hardest for a human to interpret because it's entirely machine native.
It is. It's memory carried implicitly in the model's internal representations, the hidden states, embeddings, or that raw KV cache. It's human unreadable, but incredibly efficient for the machine.
And we categorize this by its origin.
Right. First is generate. Here, an auxiliary model produces a new, compressed, latent representation to summarize the context.
Can you give me an example of that?
Sure. Think of GIST tokens, or softcot. They generate these compact soft tokens that represent the essence of a very long raw input. This avoids having to reprocess the full text over and over.
So it's like writing a quick summary for itself.
Nice. Exactly. And it's used heavily in multimodal systems like COMM or TimeVLM, where you have these huge streams of visual or audio data that need immediate compact summarization.
Okay, then we have reuse.
Reuse is the simplest one. It's just carrying over the raw prior computational states, primarily the raw KV cache, directly into the next operation. Systems like memorizing transformers do this.
What's the trade-off?
High fidelity, because nothing is compressed. But the downside is that those raw KV caches grow incredibly fast. It's like carrying every single piece of scrap paper you've ever used into the next meeting.
Which would be a lot. And that naturally leads to the third form, which must be transform.
Transform is necessary to address that bloat. It means modifying or compressing the existing latent states through selection or aggregation. Systems like SnapKV or PyramidKV, they're designed to compress that KV cache by keeping only the most influential tokens.
So they're trimming the fat.
They're trimming the fat, reducing storage costs, while trying to retain the most salient information.
Wow. Okay. This is a true deep dive. We've got three vastly different architectural forms: token, parametric, and latent, each with its own variations. So what does this all mean for someone building an agent? How do designers choose the right memory system?
Right. This is where we connect the form to the function and the dynamics. This is the core engineering trade-off. The choice reflects the behavior you want, the accountability you need, and critically, how quickly the memory needs to evolve.
Let's start with token-level memory. We said it's symbolic and transparent. So what are its ideal functions?
Well, it's transparency and it's swift, simple updating. I mean, the update dynamic is basically just appending a string, make it ideal for long-lived, high-stakes domains.
Legal, financial, medical.
Exactly. Personalized agents where you need accountability, verifiable memory provenance, and continuous, stable evolution. Agents like RecMind thrive here because you can audit the facts the agent is using. The update cost is trivial, so it's the most stable, dynamic choice.
I hear the elegance of that taxonomy, but for the average developer, isn't latent memory, despite being efficient, just too much of a black box to trust in a production system?
And that friction is exactly why you don't typically see latent memory in those legal or medical apps. It prioritizes performance and scalability over direct interpretability. Its function is high efficiency and convenient modality fusion.
So it's for court.
It's the go-to choice for multimodal architectures like XMEM that have to handle streams of complex non-textual data, or for on-device deployment where low latency and token efficiency are everything. The update dynamic is moderate, but the reward is high throughput.
Okay, and what about parametric memory? This one seems to sit in the middle. It offers great generalization, but it carries that big catastrophic forgetting risk.
That's right. Parametric memory is implicit, it's highly generalizable, but it has the highest dynamic cost to update, especially internal parametric memory, which needs retraining or fine-tuning.
So its function is best suited for what?
For tasks requiring structural insight and deeply ingrained behavioral patterns, where the need to generalize a skill outweighs the risk of forgetting a few specifics.
For example, role-playing, or maybe tasks that require complex mathematical reasoning or coding. The agent needs to know how to code in general, not just remember one specific function it wrote last week.
Precisely. If generalization of skill is the primary goal, parametric memory is the choice. If accountability and verifiable evolution are the goals, you go to token. If machine efficiency and scale are the goals, you look at latent forms.
This systematic view forms, functions, and dynamics is just incredibly clarifying. It really shows that AI agent memory is so far from being a monolithic concept. It's a toolkit.
It's a toolkit of architectural forms tailored for specific capabilities, and they all evolve differently over time.
And looking ahead, where is the research going?
Well, it's already moving beyond just single agents. The survey we looked at highlights several promising frontiers. One is shared memory in multi-agent systems.
So agents that can learn from each other?
Exactly. We need to move beyond agents with these isolated memories to shared cognitive substrates for effective collaboration. A system like G-Memory allows agents to pool and share experiences and insights in a coordinated way.
That feels like the next logical step toward complex AI societies, doesn't it? When they can start learning from each other's mistakes, not just their own.
Absolutely. And tied to that need for accountability we talked about, the concept of trustworthy memory is also critical. We have to extend ideas from trustworthy RG to make sure that the memory, whatever form it takes, is reliable, verifiable, and free from adversarial manipulation.
This whole discussion, it really raises a bigger question, one that ties back to the very foundation of intelligence itself, and that's the future direction of
Right.
human cognitive connections.
Right. The research is just beginning to explore how insights from neuroscience and cognitive psychology can inform the design of these systems. I mean, if you look at memory in humans, it's incredibly complex and multi-layered. We separate context, experience, knowledge declarative versus procedural, short-term versus long-term in these really sophisticated ways.
So the question for you, the listener, to think about is this. For AI agents to truly reach something like AGI, how closely might their memory models eventually need to mirror the intricate, specialized, multi-layered organization of the human brain?
If you look at the brain, memory isn't just one database, it's a whole collection of specialized, dynamically interacting systems. Is that complexity the necessary cost for true intelligence? I think that's a question that's going to drive the next decade of AI research.